These are the frequently asked questions for Algebra 2 for Section 7.3, Day 2. I'm going to start right here with graphing. And we have graph each function on the same set of axes. So what they're really wanting us to notice is how the graphs for the logarithms compare to the graphs of the powers that we have with unknown exponents. So what they're wanting us to see is that reflection in the line y equals x. Starting with number 36, what we would want to do is reverse this so that we can use our snail shell pattern to get that into the exponential form that we can understand. So 2 to the y equals x. Now again, what that means is that our x's and y's have completely made a role reversal here. What our inputs become our y's. So as we look at this and just put some numbers in, we realize to the -2 power is going to give us 1/4. And then if we have to the -1 power, that's going to be 1/2. If we use 0, we're going to get 1. If we put a 1 in there, we get 2. And if we put a 2 in, we get 4. And you might go one step further and get 3/8, just so that you can see enough of the curve to graph this. So at 1/4, we're at -2. At 1/2, we're at -1. At 1, we're at 0. At 2, we're at 1. At 4, we're at 2. And at 8, we're at 3. And there is our logarithm graph, which again, you can see, definitely appears to be the inverse of a normal growth curve as we go through it. And when we get to 37, that's the one we're doing. So this is y equals the logarithm base 2 of x. And now in 37, we have that format of y equals a times b to the x that we like. So we have 0, 1 as a point, 1, 2 as a point. And again, you might just think of a couple of these in a table, but remember, logarithms are what reverse the x and the y's, not any of our growth formulas. We've been graphing these all along. So if we put in a -1, we get 1/2. Maybe put in a 2 and get 4, and a 3 and get 8, because they want us to see that reflection in line y equals x. So -1 and 1/2, and then 2 and 4, and 3 and 8. And we can actually see that that's the reflection in the line y equals x. Again, the line y equals x goes through 1, 1, 2, 2, 3, 3, 3, that perfect diagonal through first and third quadrant. So there are the first two of these. And then they switch the base, so we can get a look at these. So for number 38, we reverse it and snail shell. And then we make our, all right, now I'm going to make a table. And role reversal here. In fact, I might start with -3 here because the roles are reversed for our x's and our y's. So 1/2 to the -3 is going to flip it and raise it to the third power, so it'll be 2 to the third, which is 8. 1/2 to the -2 will flip it and square it. That's 4. To the -1 will be 2. Anything to the 0 power is 1. The first power is 1/2, and the second power is 1/4. So we have 8, -3. I better move this up so you can see all of that. Then we have 4, -2. 2, -1. 1, 0, 1/2, 1, 1/4, 2, and we can definitely see what's going on with this logarithm at this point. So that one is y equals logarithm base 1/2 of x. One more to go. So y equals 1/2 to the x. We're going to go ahead and, again, this time it's straightforward. Just make your x as your input. And to the -2 power, we would flip it and then square it. -1 power is flipping it. Anything to the 0 power is 1, to the first power is 1/2, and to the second power is 1/4. And as you look at these, you should look at 36 and 37 at your tables and realize, hey, the x's became the y's, and now 38 and 39, hey, the x's became the y's. And yes, absolutely. Like I said, logarithms are just such a pure inverse. It's just nice to see all of it come together. So we have -2, 4. Then we have -1, 2. Again, we know that if we reverse that -3 from number 38, we'll have -3, 8. So I might as well put that one up there while I'm at it. 0, 1, 1, 1/2, and 2, 1/4. And that is y equals 1/2 to the x. So a lot of things they wanted us to see out of this, but mostly what they wanted us to see was the reflection through the line y equals x. And in our tables, we can definitely see that the x truly does become the y. That's why I really admire logarithms in the ability to be a complete inverse. Then number 42, this one is describe. I'm going to move that down so you can see it. Describe how the graph of each function compares with the graph of the parent function y equals logarithm base b of x. And then our instructions for this one were that you should just go ahead and graph this as well. So I'm going to grab some graph paper while I'm thinking of it here so I don't forget that part. So we're going to talk about our A, H, and K pieces, but then we're also going to graph it in the end. So we want to know about all of those shifts that we see when we go through this process. Pardon me. So 42, y equals logarithm base b of x minus h plus k. H is 5, which means in the end I'm going to have to move this right 5 units. And k is 3, which indicates that we're going to move this up 3 units. So my parent function would be y equals the logarithm base 3 of x. And I would want to reverse that so I can snail shell it. And it will say 3 to the y equals x. So again, we have that role reversal where what we have to do is input the y's to get our x's. So 3 to the -2 will be 1/9. 3 to the -1 will be 1/3. Anything to the 0 power is 1. To the first power is 3, second power is 9, third power is 27. And that's just to give you a feel for how quickly this is going up in that instance. So let's see here. We have 1/9, -2. Then we have 1/3, -1. It's graphing a little high again here. There we go. So 1/3, -1. And then we have 1, 0, 3, 1, and 9, 2. All right, so that's the shape of our graph. But now what we have to do is go right 5 and up 3. And while we're doing that, we can think about, domain and range here. Well, our domain is x is greater than 0. But now I'm going to have to shift this 5 units to the right, which means I'm going to have a new asymptote right here. At y equals 5. And up and down, well, we have arrows going up and down forever here, so that's going to be all real numbers. So it's definitely the h here that's going to make the difference. So now I want to go ahead and move my graph right 5 and up 3. about there. Like so. And there it is. And again, we definitely can do domain and range here. Domain is the x's are greater than 5, and then we have a range of all real numbers. So that's the reason we wanted you to graph these so you can get a feel for domain and range. Then number 46 is write each equation in exponential form, and I just wanted everybody to remember that that's our snail shell process, backwards. B to the y equals x. So you find your base, and in this case the base is 2. So logarithm base 2 of 128, you think about where did that 128 come from, and that is really our answer here. It's what we had for an answer when we evaluate. And then that gives you that power that you need from snail shelling. So write each equation in exponential form. Do the snail shell piece. 2 to the 7th equals 128. So we're finding out the right way to write this so our brains can understand logarithms at this point. So you're just snail shelling. That's all you need to do here. Get it in that exponential form. Then 65, put this down so you can read that. Find the inverse of each function. Remember, there's 2 basic steps. We switch the x and the y, and then we solve for y. So in 65, I'm going to switch the x and the y. And then I have to solve for y. Now, solving for y with logarithms means we need to snail shell. There's no base here. Remember we talked yesterday about how if there's no base, this is called the common logarithm, and the base is really 10 because our number system is a base 10 system. So 10 to the x equals y plus 1, and then we would subtract 1 from both sides. So 10 to the x minus 1 equals y is the inverse of that function in number 65. Next one up is 67. So switch the x and the y. Reverse the order. And snail shell. So 2 to the x equals 4y. Divide by 4. So now this is an interesting problem because this one really isn't done yet. I took a second to stop and check your book to see if they really stopped there, but because we shouldn't. But since you're just learning, I was worried that the authors of the book might go ahead and let you leave it like that. Because our bases here, for both our numerator and our denominator, are going to be 2. You could just write 4 as 2 squared. And then if you have similar bases and you're dividing, you subtract exponents. So this would be 2 to the x minus 2 equals y. So that would be the correct way to go about that problem, making sure that you've covered everything that we know, as far as rules go for powers from chapter 6 and chapter 7. Number 69 says graph each logarithmic function, and what I have to do so that I can graph it is I need to snail shell. So what I have to do here is I have to remember that if there is no base, that is a common logarithm, and that's base 10. So 10 to the y equals 2x. Well, I want to be able to use my y's as my input and get my output as x. So that would mean I need to go ahead and divide both sides by 2, or write this as 1/2 times 10 to the y equals x. It doesn't make any difference which way you do it. You just have to remember the key is that your inputs now are going to be in your y's. All right, so we go ahead and raise our 10 to the negative 2. That would be 1/100th. 1/2 times 1/100th is 1/200th. That is going to be very small. So the negative 1 power, 10 to the negative 1 is 1/10. 1/10 times 1/2 is 1/20th. Anything to the 0 power is 1, so 10 to the 0 power will be 1 times 1/2, which is 1/2. 10 to the first is 10, and 10 times 1/2 is 5. And then if we put a 2 in there, we have 100, and half of 100 is 50. So with this one, I'm really tempted to go by tens, and I think I'm going to. Not on the y-axis, but on the x-axis, so that we can get a good look at what's going on. Maybe I'll just go by fives. So this will be 10, 20, 30, 40, and 50, but then just keeping the y-axis the same. So 1/200 -2 is almost right on top of the x-axis there. And then 1/20 -1 is about the same thing. And then we have 1/2 0 and 5 1 and 52. And all it said was graph each logarithmic function. There it is. So again, domain and range wise, our domain would be x is greater than 0, and our range would be all real numbers. Then this one is all about domain and range. So in number 75, you want to think y equals logarithm base b of x minus h plus k. And our h here is going to be 3, which would have us shifting this graph 3 to the right. Now, that's going to change our domain, because h is what's responsible for that right and left shift. That's also responsible for our asymptote. So our new asymptote for this graph is going to be x equals 3, the vertical line x equals 3. And that means our domain is going to be x is greater than 3. Our range for all of these is always all real numbers. And again, that's because we have our arrows going up and down forever, but we do not necessarily use all of the x values. Then number 77, it explains how we can write, if we had 5 to the third equals 125, because logarithms are inverses. What we do is we say, all right, you know what, this is what I have right now. And I want to get rid of the 5. But in order to get rid of the 5, I have to take the logarithm base 5 of the left-hand side. Whatever we do to the left-hand side, we have to do to the right. It doesn't matter what the operation is. That is our rule of balance in algebra. So over here, those 5s are going to cancel out, and we will get 3 equals logarithm base 5 of 125. So it's another way to think through, how do I write these exponential statements as logarithms. It's just another way to think through it. And it is the way that helps us to solve them in the end. So let me go to number 77, where we have 3 to the 4th equals 81. Now, to get rid of that 3, I'm going to have to take the logarithm base 3 of both sides. Now, these are inverses because both bases are 3's, and those drop out. So we get 4 equals the logarithm base 3 of 81. And like I said, sometimes that's considered a little faster than thinking through the snail shell method as you go through there. But either way, we will get it by doing one or the other. And that is it for this video.